Grüß Gott and a warm welcome. My name is Gerhard Müller. I am the head of the Chair of Structural Mechanics here at the Technische Universität München in Munich, Germany. In our institute, we deal with vibroacoustic problems ranging from structures in civil engineering to components of the automotive industry. In order to tackle those problems, we need strong models. The models have to be designed such that they are able to describe the relevant phenomena, typically using mathematical equations. The Lamé equation, for example, permits to describe the wave propagation in the soil caused by a train passage. Here you can see how the soil is shaking. Of course, our models are not able to describe the world as a whole. The reality is reduced by them to the important aspects of the problems we are dealing with. This can be, for example, the model of a bridge that is loaded by pedestrians. We create a model, predict the vibration and check the results to ensure that the students cannot destroy the bridge by jumping and shaking. As we have measurements of the real structure, we can even compare them now with the results obtained with our model in order to calibrate it. In contrast to real structures, investigations can also be carried out at model structures in our laboratories. Look, our colleagues are playing. No, they don't play. They are doing research. They check in how far the models they developed fit to the measurement results at the model train, with which the typical train-induced dynamic forces, ranging from the regular passing of the sleepers to the roughness of the wheel or the irregularities in the track, can be assessed. We, the engineers, are able to predict important parts of real life with clever mathematical models in order to optimize our structures and to predict the responses of our systems. Feel invited to join our programs at the Technische Universität München. Welcome, dear students, to our sessions on models in civil engineering from cardiology to fishery. In our today's session, we will deal about the aspect of fishery, regarding the issue, the observation that in Arctic regions, fishermen can hear the thickness of ice when ice cracks, or in the case that somebody jumps on the ice in their vicinity. So why can they hear the thickness of the ice? In order to understand this, we should model the whole problem into its different components. So on one hand side, we have an acoustic fluid where sound is propagating and which transports energy to the ears of the fisherman. Why is energy transported to the ear of the fisherman? Because energy is propagating in the ice, which we will model as a plate in bending, excited by some jumping person, which induces impulses into the structure. So our today's task is to split this problem into its different components. First of all, we will talk about the plates in bending, which will remind you of the things you have learned about beams in technical mechanics in your previous studies. Secondly, we will then focus on the wave propagation in such beam-like structures or in plates, which is very similar. Thirdly, then we will deal with the issues of wave propagation in acoustic fluids, where the sound energy is transported to the ears of the fisherman. Point 4, we will try to understand how the sound radiation in the air takes place. In order to understand all these elements, we also have to focus on the issues of Fourier analysis and spectral analysis, which I will address very briefly in the presentation. So let's start with the plate in bending. You see here a plate which is described by a coordinate system x and y. Perpendicular to the plate we have the coordinate z. The plate has some thickness which is given by the value t. It has a Young's modulus E and a Poisson ratio nu. Out of these values, in the scope of the Kirchhoff plate theory, a bending stiffness, which is given by this formula, can be derived. Furthermore, the plate has a mass, and the mass is described by the value μ, which is nothing else but the density times the thickness of the plate. So it has a dimension of something like kilogram per square meter. The plate then is described by the so-called Kirchhoff model, which I will not address in detail. You probably have heard about that in your courses of technical mechanics. So this differential equation, a partial differential equation of order 4, has different elements. It has partial derivatives of the displacement of the plate in the perpendicular direction, w, with respect to the x and to the y coordinate. And it also has a partial derivative with respect to the time, where the inertia effects of the plates are represented. On the right-hand side, you have some load, which is exciting the plate in the z direction, p of x and y and t. So in order to solve this differential equation elegantly, we make an approach which is, for the experts among you, based on a Fourier transformation. For those who are not familiar with that, they just should assume that all the solutions and the excitations are described by a superposition of sine and cosine functions with respect to x, to y, and to the time t. For those who are familiar with complex values, they know that such functions can be nicely described by this Euler formula, or you can also describe them in such a way. We, however, in the following will stick to this type of representation. Taking this harmonic approach and putting it in the partial differential equation, we obtain a simple algebraic equation which links the load with the displacement by such a formula. The elements of the solution can be visualized by propagating waves in the plate, and if we take a beam in the one dimension of a beam. These waves have a certain wavelength, which is given here, and this wavelength is called lambda. If we describe the function with respect to time, this lambda corresponds to the period of vibration, which typically is described by capital T and can be calculated out of 2 pi over omega. You also see that out of a superposition of these oscillating functions, we can construct a standing wave, like you see here with the black line, which we observe in delimited plates. However, we now consider an infinite plate. We consider the ice, which is excited by the jumping person. So if we now take the ice without an external load, we can skip the right-hand side of the differential equation, where originally we had the load, and we place a 0 on the right-hand side. Such an approach now leads to the ratio of the wave numbers kx and ky and the angular frequency of oscillation omega, which you see here. One can show, and I don't show it here explicitly because it would take too much time, but you can try to understand this on your own, that the combination of the wave numbers kx and ky can be interpreted as a wave number kb, which is somehow inclined with respect to the x and the y coordinates of the plate. And we thus obtain now a ratio between this wave number kb and the angular frequency omega, which is given by the quotient of the mass per surface area and the bending stiffness of the plate. Putting those things together and knowing about the relation between the wave velocity of the propagating waves, like we have in the two directions, the wave length and the frequency of oscillation, we finally obtain a nice relationship between the bending wave velocity, the angular frequency, the bending stiffness, and the mass per surface of the plate, which will be decisive for the understanding of the phenomena we are dealing with. If we draw now this bending wave velocity with respect to the angular frequency, you will see that we have here a function which depends on the frequency. We call this phenomenon as dispersion of the bending wave, and we also can draw a function of the bending wavelength with respect to the frequency, which you see here on the right hand side of this picture. Now, taking some load which is exciting a plate, we then can see here different patterns depending on the frequency of excitation, and you see here for higher frequencies we have shorter wavelengths like on the right hand side, and for lower frequencies we have larger wavelengths as results for our harmonic single load exciting such a plate. Now we have described the plate satisfactorily, and now we go on to the acoustic fluid. In order to understand what happens in the acoustic fluid once a plate at the delimiter xy at some plane of this acoustic fluid is exciting the fluid. So again, we take in the first step the partial differential equation which can be derived for the acoustic fluid. You have here in this partial differential equation on one hand side the acoustic pressure describing the acoustic situation in the fluid, and on the other hand side you also have here the wave velocity, the speed of sound in the acoustic fluid, which we call C sub A. This differential equation now can be solved with a similar approach where we again describe the pressure with respect to the x coordinate, the y coordinate and the time by harmonic approaches with the wave number kx, ky and the angular frequency omega. So what remains is now one element which is described by EI kz, and the question now is what is the character of this element, and this character will be decisive for our problem, I can promise you already now. Now what can we do? We now place this approach in the differential equation, and you will see that the first element, the second element and the last element, the fourth element, will simplify considerably, and also the third element will simplify by this multiplicator with the value kz, and we have a simple equation with which we can calculate this value kz describing the behavior of the solution in the z direction. So the question now is, what is this behavior like? So our new approach is given in this form, and you see here we have in the z direction a certain element which we will discuss now a little more in detail. We abbreviate this element now by substituting this element by Ka, the wave number in the air. Now, taking these forms, we now realize that the solution in the z direction depends considerably on this value Ka compared to the values Kx square and Ky square. In the following way: in the case 1, when Ka square is larger than Kx square plus Ky square, we obtain in the z direction a solution which again is harmonic. That means that we have in the z direction also a sinus and cosinusoidal dependency of the pressure with respect to z. One can now show that this solution is linked with a wave which is propagating under a certain inclination from the plate into the fluid, and this wave can be described by cosine and sine function with respect to z. In the second case, when Ka square is smaller than Kx square plus Ky square, the exponent of the exponential function becomes real. And as you know, a negative real exponent is linked with a decaying function, which you see here. That means that the pressure decays from the xy plane, and if the person, the fisherman standing here, has such a size, he will probably not hear the sound field anymore, whereas if he's standing here in this wave pattern, he will be fully affected by the sound field which is propagating from the plate. The first case we call propagating waves or far fields. The second case we call evanescent fields or near fields of this radiation problem. That means that just under certain circumstances, namely in case that the bending wave length, which is given here, lambda b, is larger than the wavelength in the air, which I call here lambda a, we have this radiation phenomena. In the other case, if the bending wave length gets smaller, shorter than the wavelength in the air, we will have evanescent fields which just cause near fields which radiate very poorly. In the limit case, when both wavelengths are equal, or in other words, when the dispersive bending wave velocity is equal to the non-dispersive speed of sound in the air, we have the so-called critical frequency, and this critical frequency is then decisive to decide whether the problem radiates or whether it radiates not really. So let's couple now the air with the plate, and you see that the speed of sound in the plate, CB, and the speed of sound in the air, CA, will cross at a certain critical frequency at this limit case. Above this critical frequency, the bending wavelength is longer than the wavelength in the air, and we have a radiation of sound. Below, we have these evanescent fields. And depending on the thickness of the plate, you see here different crossing points, different critical frequencies. And this means that at the basis of the critical frequency, you can deduce the thickness of the plate. Now we have described the plate, we have described the fluid, and now we should focus a little on the load. And as you probably know from your courses, we can look at an impulse load and describe the frequency content of an impulse load by taking the impulse load, assuming that this impulse load repeats after a certain while t, and then carrying out a frequency analysis, which is also called Fourier analysis. We make a Fourier series for this load. The Fourier series is given here, so you can cross-check it on your own if you are interested in. And if we have one single event, we can increase this t towards infinity, and we come from the Fourier series to a Fourier integral to the Fourier transformation, which shows that the load P of t, which is a very short impulsive load, can also be described in the frequency content by a P of omega with constant values independent of the frequency, so constant over the frequency range. So this means that by this impulse, or also by the crack, we will have a very broad band excitation from high to low frequencies. So now let's conclude. Our excitation contains, in an ideal case, all frequencies. Just above a certain frequency, F larger than F critical, sound is radiated and can be heard by the fisherman. The high frequencies are linked with a higher bending wave velocity, and they can be perceived earlier at the different locations. The lowest frequency, which is linked with a strong radiation of sound, is the critical frequency. The critical frequency depends on the thickness of the ice layer. So, of course, if we can detect the critical frequency, if we can hear the critical frequency and describe it, we can deduce from it the thickness of the ice. Let's go to an example. So here you have two different thicknesses of the ice, and in the first case, which is shown here, the ice would sound like that, starting at high frequencies and finishing at a certain critical frequency, where the speed of the bending wave is equal to the speed of sound. In the second case, the other type of ice will have its critical frequency here, and then you will hear a kind of different sound. Let's hear the first sound. Let's hear the second sound. So now we come to the task, and we would like to think about the following problem. So we have two different types of eyes, a layer 1 and a layer 2. Let's listen to layer 1. Let's listen to layer 2. Unless you have an absolute hearing, you will not be able to tell us what is the frequency the signal finished in its process. So let's measure it. So we measure the first layer and we measure the second layer. You see here on the left-hand side the description of the sound pressure versus time, and frankly speaking, you see nothing. So in order to analyze those signals, you should make a Fourier transformation, which is done here, and represent the signals in the frequency domain. And you see here that the red signal, the upper signal, has a frequency content which finishes approximately here around 250 Hertz. Whereas the green signal has a frequency content which finishes approximately here around 1500 Hertz. So you know now the frequency limit of the perceived sound. On the other hand side now, you also have some assumptions concerning the Young's modulus, which is given here, the density, which is given here, the wave velocity, the speed of sound in the air, and the Poisson ratio. So with these values, you should now be able to assess the thickness of the eyes, knowing the lower frequency of the perceived sound. The question now is whether this model you applied here is conservative or not. You should for this assume in the whole process of our derivation which elements we neglected. There was one important element which we didn't take into account. You should think about that. Which element was that? And then I would also like to draw your attention to the results that have been published by Lundmark in the year 2001, who correlated the thickness of eyes with the perception of fishermen who had the ability of absolute frequency perception. For the experts among you, for those who know the differential equation of the Kirchhoff plate and also know the relevance of the different elements, I would like to ask you to estimate the stiffness of the water using the model of an elastically supported plate, comparing your results with the results obtained by Lundmark. You then can get a feeling of the limits of your model, and you can also get a feeling of how models can be calibrated by measurement results. I hope you have enjoyed this short course. We wish you valuable insights in solving the task, good solutions. We are looking forward to see your solutions, and we finally wish you a nice rest of the day.